Night in the southern hemisphere has a different kind of quiet. It isn't the silence of an empty room, or even the hush that settles over a sleeping city. It's deeper, older, something that feels woven into the land itself, as if the darkness here has been watching the sky far longer than humans have had names for anything above it. Imagine yourself standing somewhere open and breathless, a desert plateau in Chile, a lonely stretch of outback, a wind-carved field in Patagonia where the cold bites your fingers just enough to remind you that you're alive. The horizon is low and clean, and the sky climbs straight upward. No haze, no light pollution, nothing to dilute what the universe has chosen to show tonight. And then, as your eyes adjust, you notice them. Two pale smudges hanging off to the side of the Milky Way. Not stars, not clouds, not anything you were expecting. They look almost like faint smoke. A pair of ghostly stains brushed across the darkness. The large Magellanic Cloud, the small Magellanic Cloud. Two galaxies drifting in the night like lost lanterns. They don't jump out at you the way Orion does in the north, or the way the Southern Cross suddenly snaps into focus with its clean geometry. The Magellanic Clouds are softer, shy almost. They're the kind of thing you only notice if the world around you becomes quiet enough to let them speak. And when they do, there's something strangely intimate about it. These aren't distant points of light. They're shapes, real shapes, visible to the naked eye, floating 160,000 and 200,000 light-years away. You're seeing entire galaxies without a telescope, entire cosmic systems. Hundreds of millions of stars, clusters, nebula, all smoothed together into a gentle glow that looks nothing like the spirals we see in textbooks. It's no wonder that for most of human history, nobody thought of them as galaxies. That word didn't even exist until modern astronomy forced us to expand our vocabulary. To ancient eyes, to the eyes of anyone standing here tonight, the Magellanic Clouds feel closer to weather than to astrophysics. They resemble the wisps of daylight clouds that linger after sunset, except they never move, never fade, and never quite resolve into anything sharper. Their light is diffuse, like the glow of a lantern seen through mist, soft around the edges, impossibly delicate. And this delicate glow has been part of the human experience for tens of thousands of years. Long before telescopes, long before cities, long before stories were written down. People saw them. People navigated by them. People attached meaning to them, practical, spiritual, emotional. They were constant companions for anyone living below the equator, or anywhere far enough south that the Milky Way itself felt like a river running directly overhead. What's remarkable is that the Magellanic Clouds aren't subtle once you know they're there. You don't need dark-adapted eyes or special conditions. They're as obvious as the Milky Way itself, if you live in a place that still allows the night to belong to the sky instead of the streetlights. Ancient Polynesian navigators knew them well. Aboriginal Australians embedded them into constellations of dark space, creatures outlined not by stars but by the shadows between them. The Inca associated their pale, cloudy glow with celestial animals. To them, these weren't galaxies. They were landmarks in the sky, guides, symbols, pieces of the night that always returned. Even the first European sailors who reported them didn't fully grasp their scale. Antonio Pigafetta, writing during Magellan's voyage around 1520, simply noted them as two little clouds. Two little clouds, he called them, because what else could they be? You can't fault him for that. When your only instrument is the naked eye, and the idea of other galaxies doesn't exist yet, then yes, they look like clouds. And even now, standing under them with a modern understanding of what they are, the mind struggles with the scale. These faint patches of light look small enough to cover with your thumb, held at arm's length. But they are enormous, sprawling dwarf galaxies orbiting our own. Yet they don't look like galaxies. Not remotely, not the way we imagine them from pages and screens. A spiral galaxy has structure, arms, bulges, lines of symmetry. It announces itself. But the Magellanic Clouds are irregular, incomplete, as if sculpted from pieces of something that refuse to fit neatly together. The LMC has hints of a bar, but the rest of its body feels stretched, warped, tugged by gravitational tides it can't escape. The SMC looks even more ragged, its shape twisted by repeated encounters with the larger galaxy beside it, and the enormous halo of dark matter that surrounds them both. But you wouldn't know any of that from looking. From here, they're just two ghostly smudges. And maybe that's part of their beauty. There's something compelling about a galaxy that doesn't flaunt its identity. A galaxy that prefers to arrive quietly, offering no immediate explanation. A galaxy that whispers instead of shouts. It's a reminder that not everything cosmic demands attention. Some things simply exist, softly, patiently, waiting for us to notice. And standing beneath them now, with the cold night air brushing your skin and the Milky Way arcing overhead, you feel the presence of those two pale lights as something almost personal, as if they're not just objects in space, but companions, familiar faces that have looked down on humanity since the beginning. Before we go deeper, if you enjoy exploring the quiet wonders of the cosmos like this, consider subscribing and leave a comment telling me where you're listening from and what time it is there. It helps this channel grow, and it keeps these journeys alive. Now the eye returns to those distant smudges, and the mind begins to wonder, what are they, truly? How did they form? Why do they look the way they do? And what stories do they carry across the void to reach us? The night holds its breath again, and the two ghosts drift quietly above the horizon, waiting for us to follow. Most people never get to see a galaxy with the naked eye. They see stars scattered like grains of salt. They see planets if they know where to look. They see meteors, satellites, the pale band of the Milky Way. But galaxies, those usually require technology, lenses, CCD sensors, observatories perched on mountains where humidity gives up the fight. And yet, here in the southern sky, two galaxies hang in plain sight. Not bright, not dramatic, but unmistakably there if you let your eyes soften for a moment. The large Magellanic Cloud and the small Magellanic Cloud, our two most accessible galactic neighbours. They are, by classification, dwarf irregular galaxies, a description that sounds more like an insult than a scientific definition. Irregular suggests a lack of organisation, as if the universe assembled them on a Monday morning when it hadn't had enough coffee. But in truth, irregular galaxies are simply galaxies whose shapes have been reshaped, sometimes violently, by their environments, interactions, gravitational tugs, close calls with giants like the Milky Way. They're cosmic survivors, not cosmic mistakes. The large Magellanic Cloud hangs about 160,000 light-years away, a mere whisper in cosmic terms, especially when the Andromeda Galaxy sits 2.5 million light-years beyond. The small Magellanic Cloud is just a little farther, around 200,000 light-years distant. Both lie in what we call the Milky Way's outer halo, the vast, dimly populated region that envelops our galaxy like a loose cloud of stars, gas, and dark matter. Even their distances tell a story. They're close enough to be gravitationally entangled with us, yet far enough to hold onto their identities. For now, the large Magellanic Cloud, let's call it the LMC for simplicity, is the bigger of the two. It stretches roughly 14,000 light-years across. Though its outer regions are diffuse and hard to measure sharply, it holds on the order of 10 billion solar masses of material. Not much if you compare it to the Milky Way's trillion-plus solar masses, but substantial for a dwarf galaxy. The small Magellanic Cloud, the SMC, is more modest. It spans around 7,000 light-years and contains perhaps 3 billion solar masses. Think of the LMC and SMC not as miniature spirals, but as star-filled islands. Beautiful, but lacking the symmetry and order that larger galaxies develop over billions of years. Their irregular shapes are one of the first clues that they've lived unsettled lives. Spiral galaxies form their elegant arms through a delicate interplay of rotation and density waves, like the slow, repeated motion of a potter shaping clay. Elliptical galaxies, on the other hand, are the aftermath of ancient collisions, smooth and spheroidal, with stars that race around in all directions like bees in a disturbed hive. But the Magellanic Clouds are neither. They have no grand spirals, no luminous bulges, no clean outlines. Instead, their structures look as though someone took a normal galaxy, pressed on it unevenly, and let gravity do the rest. They are lopsided, asymmetrical, and in places visibly stretched, especially the SMC, whose distorted appearance is a direct consequence of interacting with both the LMC and the Milky Way's gravitational pull. The LMC does, however, possess what astronomers would call a bar, a dense, elongated region of stars near its centre. But even this bar is off-centre, misaligned, as if the galaxy couldn't quite decide where its middle should be. Why? Because the LMC isn't a stable, isolated galaxy. It's constantly being pushed and pulled, not only by the Milky Way, but by the small Magellanic Cloud, with which it has danced a gravitational tango for billions of years. Their relationship is messy, beautiful, but messy. One of the most revealing features inside the LMC is the Tarantula Nebula, or 30 Doradus, an enormous star-forming region so bright that if it were placed at the same distance as the Orion Nebula, our night sky would glow like a science fiction backdrop. Inside it lies 136, a young cluster containing some of the most massive stars ever discovered. Stars dozens or even hundreds of times the mass of the Sun, blazing with ferocity that shortens their lives to a few million years at most. This is not typical for dwarf galaxies. The LMC is unusually active, unusually vibrant. The SMC, though quieter, also contains pockets where gas collapses into new stars. But its star-forming regions are smaller, more scattered, less dramatic. The SMC is like a younger sibling, living in the shadow of a more extroverted older one, still interesting, still full of surprises, but without the show-stopping nebulae that make the LMC one of the most studied star nurseries in the local group. The stellar populations of the clouds reflect their chaotic histories. They contain ancient stars, globular clusters more than 10 billion years old, as well as newborn stars so young they barely qualify as stars at all. Their metallicities, that is, the amount of elements heavier than hydrogen and helium, are significantly lower than the Milky Way's. In astronomy, this is a sign of youth, or at least slower chemical evolution. The clouds haven't been forming stars continuously. Instead, their star formation happens in bursts, triggered by gravitational interactions. When two galaxies brush past one another, their gas can be compressed just enough to ignite new generations of stars. And the Magellanic Clouds have been brushing past each other for a very, very long time. Their shapes, their metallicities, their gas content, even their current star formation, all of it is written in the gravitational handwriting of their past encounters. To understand why they look the way they do, imagine a spiral galaxy like the Milky Way as a vinyl record spinning smoothly, its grooves clean and defined. Now imagine nudging that record with your hand every few minutes, tilting it slightly, pushing it off-center, letting it wobble. Eventually the structure becomes distorted. The neat spiral arms stretch. The symmetry breaks. That's the fate of small galaxies caught in the presence of giants. The LMC and SMC are essentially galaxies that never got the chance to finish their formation uninterrupted. Instead, they formed in a neighbourhood where larger galaxies continually reshaped the rules. Their chaos is their signature. Astronomers believe the LMC may even host a significant amount of invisible mass, an unusually large dark matter halo, far larger relative to its size than expected. This dark halo is so massive that it actually pulls on the Milky Way, slightly warping our galaxy's outer disk. Yes, these faint clouds in the night sky are reshaping the structure of the Milky Way itself. That might be one of the most astonishing facts about them. They may look gentle and ghost-like, but gravitationally, they are anything but insignificant. What's even more fascinating is that the LMC and SMC might not just be two galaxies. They may have once been the core members of an entire Magellanic group, a cluster of dwarf galaxies that entered the Milky Way's halo together. Several recently discovered ultra-faint dwarf galaxies appear to follow similar trajectories, suggesting they may have been siblings once, orbiting the LMC the way moons orbit a planet. If true, this would mean the Magellanic Clouds are not merely companions of the Milky Way. They are leaders of their own miniature galactic family, absorbed into ours only recently in cosmic time. And all of this complexity, dark matter halos, starburst regions, tidal interactions, satellite dwarfs, hides behind that gentle glow you see in the night sky. Nothing about their appearance hints at the violence behind the scenes. That's the strange beauty of astronomy. The most turbulent objects can masquerade as the most peaceful. When you look at the Magellanic Clouds with the naked eye, they appear as small, calm patches of milky light. They give no indication of the collisions, the gravitational shearing, the frantic starbirth, or the multi-billion-year interactions that shaped them. They hide their scars well. Their irregular shapes are not signs of immaturity, but evidence of survival. They've been stretched, disrupted, pulled apart, and yet they persist. And perhaps that's why they're so compelling, because in a universe filled with spirals that seem perfectly composed and ellipticals that have settled into their old age, the Magellanic Clouds feel alive, imperfect, in motion, galaxies that are still becoming. When we look at them, we're not just seeing what they are now, we're witnessing a snapshot in an ongoing story, one that stretches from the early universe to the far future, where their paths will one day collide more dramatically with our own. The night sky tends to give the illusion of stillness, but nothing up there is truly still. Least of all the galaxies that drift so quietly near us, carrying histories more complicated than their faint glow suggests. Two ghostly shapes, hiding the truth of their chaotic lives. Two dwarf irregular galaxies, reshaped by forces far larger than themselves. Two companions of the Milky Way, whose existence continues to influence our own. And all of it, from their distances to their distorted forms, begins to make sense once we understand what they really are. Not clouds, not nebulae, but galaxies in their own right. Galaxies that never learned to hold still. When we talk about galaxies, we usually imagine observatories, data pipelines, simulations, and scientists with doctoral degrees. But the first astronomers who studied the Magellanic Clouds didn't have instruments, charts, or metal domes under dark skies. They had their eyes, their memory, and a sky untouched by human light. For tens of thousands of years, the large and small Magellanic Clouds were not scientific objects. They were companions, familiar features, part of the everyday night. Before telescopes and astrophysics, these pale smudges shaped navigation, storytelling, and entire cosmologies. In the southern hemisphere, they were constants. They rose and set with a rhythm as reliable as the moon. They drifted across the sky with the seasons. Their brightness changed with the atmosphere, and because they looked nothing like stars, they commanded special attention. Something so large, so soft, and so persistent inevitably becomes meaningful. To modern astronomy, the Magellanic Clouds are dwarf galaxies interacting with the Milky Way. To ancient peoples, they were signposts, clues, symbols, stories, books written in light. And the cultures who lived with them developed relationships far deeper than simple observation. The first ocean travellers of the Pacific, Polynesian navigators, read the night sky the way some people read poetry. Not literally, not mechanically, but intuitively, with an understanding born from generations of memory. Their voyages, spanning thousands of kilometres of open ocean, remain among the greatest feats of human navigation. No compasses, no sextants, only the sky. For the Polynesians, the Magellanic Clouds were not galaxies. They were directional anchors, the night marks. Imagine being in a double-hulled canoe far from land, with only the swell of the Pacific beneath you and the sky above as your compass. On clear nights, the Milky Way runs overhead like a river, and off to one side float the two clouds. Their positions relative to the horizon change with latitude. Their height becomes a rough indicator of how far south or north you have travelled. This was not written down in a book. This was a knowledge carried in the mind, passed in chants, embedded in navigational lore called wayfinding. The clouds formed part of the star compass, an invisible, circular guide used by navigators to orient themselves. They knew how far above the horizon the large Magellanic Cloud sat when approaching islands like Rapa Nui or Aotearoa. They recognized how both clouds dipped lower when traveling toward equatorial seas. Some traditions describe them as celestial ovens or bowls, glowing softly across the night. Others fold them into myths of ancestral journeys. Even more remarkable is how Polynesian navigators used the dark spaces between the Milky Way and the clouds to judge cloud coverage and storm movements. They could read the faint glow as an indicator of atmospheric thickness, an early form of weather forecasting, achieved simply by paying attention to how much of the cloud's light made it through. In a world without artificial light, subtle differences become loud signals. To them, the clouds were not distant galaxies. They were tools for survival. They were proof that the sky could be trusted. Meanwhile, in Australia, the oldest continuous culture on Earth, the Magellanic Clouds held a different meaning. Aboriginal astronomy is an astonishingly rich and sophisticated system built over at least 50,000 years of sky watching. Unlike Western constellations, which rely on connecting stars with imaginary lines, many Aboriginal constellations form from the darkness, the shapes made by dust clouds within the Milky Way. But the Magellanic Clouds, standing apart from the main band of the galaxy, played their own roles in story and ceremony. Among several groups, including the Burong people of Victoria, the large Magellanic Cloud was known as Budji Bim, a spiritual being whose lava flows created the landscape. The small Magellanic Cloud was often identified as another ancestral figure or related entity. In some traditions, the two clouds represented campfires of sky spirits, embers glowing faintly as they prepared for nightly tasks. In others, they signified weather spirits whose presence foretold seasonal changes. One of the most widespread interpretations casts them as a celestial emu's eggs, glowing softly near the Milky Way's great dark emu constellation. Their brightness helped communities track the timing of important seasonal events, when to gather food, when migratory birds would appear, when certain plants would flower. The night sky was a calendar, precise and dependable. The Magellanic Clouds were part of its mechanism. What makes Aboriginal astronomy extraordinary is its longevity. These interpretations were passed orally through thousands of generations, a continuity older than any civilization, older than agriculture, older than the pyramids. The stories were not myths in the Western sense. They were knowledge systems, ecological, astronomical, social, spiritual. They encoded instructions for living and surviving in one of the most varied continents on Earth. When you stand under the southern sky today and see the clouds, you are seeing the same markers ancient peoples used to predict seasons, locate travel routes, and maintain cultural memory. That continuity puts our modern understanding into perspective. We treat the Magellanic Clouds as scientific data points. They treated them as threads in a world where sky and land are connected. Travel across the Pacific to the Andes, where the Inca Empire once stretched across thousands of kilometers of mountains, valleys, and deserts. The Inca had a sophisticated astronomical tradition built around solar cycles, lunar motions, and the dark constellations of the Milky Way. The Magellanic Clouds appear in several Inca records, often associated with animals and cosmic fertility. The Inca believed the sky's luminous and dark patterns reflected life on Earth. The clouds, faint yet distinct, were seen as celestial grazing fields or corrals for mythical animals, places where sky creatures lived and moved through the heavens. Their slow drift across seasons mirrored the movement of animals below. These interpretations weren't arbitrary stories. They shaped rituals, agricultural timing, and social festivals. And because the Inca Empire stretched across multiple latitudes, the position of the clouds became a natural marker for regional calendars. Communities further south saw the clouds higher in the sky. Communities further north saw them lower. That variation helped synchronize agricultural cycles across the empire. The Mapuche people of Chile and Argentina, one of the few indigenous groups who successfully resisted both the Inca and the Spanish, also gave deep meaning to the two clouds. Among Mapuche cosmology, the Magellanic Clouds were often interpreted as the souls of ancestors wandering through the night sky. Their hazy glow was the light of past generations guiding the living. Seeing them was a reminder that life was part of a larger journey, one that extended beyond the earth. Above was not separate from below. The sky was not a place out there. It was a continuation of the world humans walk on. This might be one of the most powerful ways humans have ever viewed galaxies, not as distant, cold clusters of stars, but as part of the community, a place where ancestors dwell, where guidance comes from, where meaning is reflected back onto the earth. The idea of the sky as a living landscape is common across indigenous cultures. The Magellanic Clouds played central roles because they are visible, stable, and unlike anything else. Their pale glow made them ideal markers for orientation. Navigators used them to infer latitude, farmers used them to track seasonal shifts, storytellers used them to weave cosmologies, communities used them to synchronize festivals, migrations, and ceremonies. One of the simplest uses was also one of the most effective. The clouds vary in brightness depending on atmospheric clarity. On dry, clear nights they shine cleanly, while on humid or dusty nights they fade. In several indigenous traditions, their visibility served as a weather indicator, a celestial barometer long before microscopes or meteorology. Others tracked how the clouds rotated around the south celestial pole. Unlike northern constellations, which appear to spin around Polaris, the southern sky has no bright star marking its pole. Instead, ancient sky watchers used the empty space between the clouds and the Southern Cross to find true south. This allowed precise orientation in environments where the landscape offered no clues. Open sea, desert plains, or windswept grasslands stretching to the horizon. If you look at the Magellanic Clouds today, you might just see faint patches of light, but to ancient cultures they were teachers. They were calendars, they were compasses, they were symbols of creation, ancestors, and the structure of the world. And perhaps most beautifully, they were reminders that the sky was something to live with, not just look at. We modern observers tend to separate scientific understanding from cultural meaning, as if the universe can only be one thing at a time. But humans have always layered interpretations. Something can be a galaxy and a symbol, a star cluster and an ancestor's fire, a dwarf, irregular system of hydrogen, dark matter, and newborn stars, and also a guide that keeps sailors from losing themselves in the ocean's night. The Magellanic Clouds have always been both. They are astrophysical objects today, but for most of human history, they were personal. They shaped stories, guided explorers, anchored ceremonies, and helped entire civilizations understand their place in the world. Under the southern sky, the past is still there. The clouds still hang in their usual places, and though we now know what they truly are, we also know what they once meant. Two pale ghosts drifting across time, carrying not just the light of distant stars, but the memories of countless human lives lived beneath them. When Europeans first sailed into the southern hemisphere, they were not only entering unfamiliar waters, they were entering an unfamiliar sky. Every degree south peeled away familiar constellations and replaced them with patterns that no sailor from Spain or Portugal had ever seen before. The night sky became a map in rearrangement. The North Star sank lower each night, and with it sank the navigational certainty these sailors had relied on for centuries. The constellations of classical Europe, Ursa Major, Cassiopeia, Draco, tilted awkwardly toward the horizon and disappeared behind the ocean's curve. And then, somewhere around the latitude of Brazil, new stars rose. The Southern Cross, the Coalsack Nebula, and hanging off the side of the Milky Way like two misplaced smudges, the faint, cloudy shapes that would eventually bear the name of the man leading this voyage, Ferdinand Magellan. But the person who wrote the first detailed Western description of them was not Magellan himself. It was his chronicler, Antonio Pigafetta, a Venetian scholar whose meticulous notes remain one of the greatest travel journals in history. Pigafetta boarded the expedition in 1519, not as a sailor, but as a writer, someone whose job was to observe, record, and translate the world for those who would never see it. His journal is one of the only surviving eyewitness accounts of that first circumnavigation of the Earth, and it contains a quiet moment where he looks up at the sky and sees something entirely new. In his notes from 1520, during the long and brutal attempt to find a passage through what is now the Strait of Magellan, Pigafetta describes the southern heavens. "We saw 2 clouds of small stars, one larger than the other near the Antarctic pole, and another star which does not move. The star which does not move was the faint southern pole marker, Sigma Octantis, but the 2 clouds of small stars are unmistakably the large and small Magellanic clouds." For Pigafetta, they were not galaxies. He didn't know what galaxies were. No one did. In the early 16th century, the word galaxy still referred only to the Milky Way. Everything outside it was assumed to be part of our own cosmic system. But Pigafetta's description is important. It is the first textual Western acknowledgement of the Magellanic Clouds as fixed, repeatable features of the southern sky. He distinguished them from passing weather, noted their stability, and recognized that they were made of small stars, not mist, even if he didn't grasp their nature. He saw them, wrote them down, and in doing so, quietly inserted them into European astronomical consciousness. So why are they named after Magellan? Naming conventions in early European science were rarely about who discovered something. They were often about who brought it into the European worldview. Magellan's voyage was the first major Western expedition into deep southern latitudes. It opened up new maritime routes and introduced European astronomers to constellations and celestial features that had been known to the southern world for tens of thousands of years. After Pigafetta published his account, cartographers began including these clouds on star maps. Navigators used them alongside the Southern Cross to orient themselves in unfamiliar waters. Scholars in Europe reading Pigafetta's descriptions began referring to them as Magellanic Nubeculi, the Magellanic Clouds. It wasn't that Magellan discovered them, it was that the voyage carrying his name introduced them into European literature. But for all the attention Pigafetta receives in Western histories, his record was not the first written description of the clouds. Nor were Europeans the first to recognize their uniqueness. Centuries before Magellan sailed, astronomers in the Islamic world had already catalogued them. Arab and Persian sky watchers, especially those navigating the Indian Ocean, saw the Magellanic Clouds in southern skies during monsoon trade voyages. They appear in the writings of Ibn al-Faqih al-Hamadani, a 10th century Persian geographer who described them as white patches near the southern pole. Even earlier references are scattered across navigational guides used by Arab sailors who travelled as far south as Zanzibar, Mozambique, and Madagascar. These sailors followed the seasonal winds, relying on latitudinal star patterns to determine how far along the African coast they had travelled. For those who ventured far enough south, the Magellanic Clouds were familiar companions, useful, stable, and easily recognisable. A 13th century astronomical manual known as the Book of Fixed Stars by Persian astronomer al-Sufi contains references to faint southern nebulosities not visible from his location but reported by sailors and travellers who ventured below the equator. Al-Sufi carefully distinguished these nebulous forms from transient clouds, marking them as astronomical phenomena. This predates Magellan's voyage by more than 500 years. The Islamic Golden Age produced some of the world's most advanced astronomical observations. Their star catalogues, including those by al-Battani and al-Sufi, were the foundation upon which European astronomy built after the Renaissance. Their navigational manuals, rutters, were used for centuries by Arab, Persian, and later Portuguese sailors. So it is historically inaccurate, even unintentionally imperialistic, to claim that Magellan or Pigafetta discovered the Magellanic Clouds. They described them for Europe, yes, but they were already documented elsewhere. And long before any written records, they were woven deeply into the traditions, calendars, and mythologies of cultures across the southern hemisphere. Still, the name stuck. The Magellanic Clouds entered European maps, and from those maps they entered scientific vocabulary. Once a name appears in star atlases and textbooks, it becomes part of the astronomical canon, difficult to undo. That's the strange thing about names in science. They can reflect cultural history more than scientific truth. We refer to the moons of Jupiter with Roman names, not because Jupiter cares, but because Western astronomers named them. We call the Orion Nebula Orion, even though the Hunter constellation is a purely cultural construct. And we call two dwarf galaxies the Magellanic Clouds, because one explorer's voyage reshaped Europe's relationship with the sky. But understanding the earlier references helps restore a more global perspective. The night sky doesn't belong to any one culture. It has been read, interpreted, mapped, and mythologized by countless communities over thousands of generations. Pigafetta's notes were simply the bridge through which Europe joined that tradition. Imagine being him for a moment, standing on the deck of a creaking wooden ship trapped in the freezing straits of Patagonia, the wind howling through the rigging, the ocean dark and hostile, supplies dwindling, crew divided, tempers fraying, the land around them bleak and unwelcoming, and overhead the calm glow of two clouds. Pigafetta must have found a kind of solace in them, a reminder that even in this hostile world, something constant remained. They were the same night after night, unaffected by storms or conflict. Perhaps that's why he wrote about them, not because they were strange, but because they were comforting. He couldn't have known he was naming them for the next 500 years of astronomy. He couldn't have known that these faint patches would become icons of the southern sky in scientific literature. He simply wrote them down because they were there, and because he felt compelled to describe the world as he saw it. History sometimes turns small observations into lasting legacies, and so the two ghostly shapes that sailors and storytellers had known for millennia became Magellanic, not because Magellan found them, but because Pigafetta took the time to look up and notice. If you look at the Magellanic Clouds with the naked eye, it's hard to imagine that inside those quiet, ghostly shapes lies some of the most explosive starbirth in the entire local group. Their pale glow gives no hint of the violence inside, no clue that these little galaxies contain regions so bright, so chaotic, and so full of young stars that even the Milky Way can't compete. And nothing captures this contrast better than a place called 30 Doradus, known more famously as the Tarantula Nebula. It sits inside the large Magellanic Cloud, like a beating heart, pumping new stars into the galaxy with a ferocity unseen in our corner of the universe. If our naked eyes could see hydrogen gas glowing at its true brightness, the Tarantula Nebula would appear in Earth's night sky brighter than Venus. The entire constellation of Orion would vanish behind it. The region is only about 1,000 light-years across, tiny on galactic scales. But inside that span lies a concentration of raw star-forming power unmatched anywhere else we've observed nearby. In the Tarantula Nebula, clouds of hydrogen collapse under their own gravity, triggering cascades of new stars. Radiation blasts carve cavities in the gas. Shockwaves from supernovas squeeze nearby clouds and spark new generations of stars. The process is as much destruction as creation, a cycle of collapse and ignition that has been going on for millions of years. The name Tarantula is well earned. Photographs reveal tendril-like filaments stretching out like the legs of some cosmic arachnid, glowing webs of ionized gas sculpted by the intense winds of massive stars. And at the center of it all sits 136, a cluster so extreme it almost defies belief. To the human eye, a star is a star, points of white light, some brighter, some dimmer, all essentially identical from our view on Earth. But inside R136, the stars are not ordinary. They are enormous, violent furnaces pushing the limits of what physics allows. Some of the stars in R136 exceed 150 times the mass of the Sun. A few push beyond 200 solar masses, something once thought to be impossible. These stars shine millions of times brighter than the Sun and burn through their fuel with such intensity that their lifetimes will be only a few million years. They will end in spectacular supernovas or perhaps even direct collapse into black holes. The cluster itself is packed so densely that if you placed our solar system inside it, the night sky would be unbearably bright. Thousands of stars would crowd the heavens. Shadows would form from multiple directions. The sky would never truly become dark. Yet from 160,000 light-years away, R136 is just a faint knot in a faint ghost in the faint haze of the LMC. That scale difference, the disconnect between what we see and what these regions truly are, defines the Magellanic Clouds. Inside these dwarf galaxies lie pockets of star formation, far more intense than anything happening in the Milky Way today. Our galaxy is a mature spiral system with star formation spread broadly across its disk. We produce roughly 1 or 2 new stars per year, maybe 3 if the galaxy is having an unusually active moment. The LMC alone, despite being a fraction of our size, creates stars at a far faster rate, especially concentrated within the Tarantula Nebula. It's like comparing a calm, slow-growing forest to a volcanic island where new land erupts constantly from the sea. But why? Why are the Magellanic Clouds such effective star factories? Part of the answer lies in metallicity, astronomy's oddly chosen word for the abundance of elements heavier than hydrogen and helium. Higher metallicity gas cools more efficiently, but it also absorbs and blocks radiation, changing the way clouds collapse. Lower metallicity gas, like that found in the Magellanic Clouds, behaves differently. It allows deeper penetration of ultraviolet light, affecting turbulence within molecular clouds. It also means that massive stars experience weaker stellar winds, letting them hold on to more mass. Low metallicity environments tend to produce more massive stars, and massive stars drive starbursts. In the Magellanic Clouds, stars form in clusters, big ones, dense ones, clusters where the ultraviolet radiation of one generation rapidly shapes the next. It's a feedback loop. Massive stars form, release energy, compress surrounding gas, and trigger more star formation. The Tarantula Nebula is the most dramatic example of this, but it's not the only one. The LMC and SMC contain dozens of star-forming regions, where this cycle unfolds on smaller scales. Another reason the clouds are so active lies in their interactions, both with each other and with the Milky Way. Galaxies don't form stars in isolation. Gravity is a sculptor. When 2 galaxies pass close to one another, their gas clouds feel the tug. They stretch, twist, compress, and compression is the first step toward collapse. The LMC and SMC have been interacting for billions of years, passing within close proximity, sometimes stripping material off each other, sometimes colliding at low angles. Each encounter leaves trails of hydrogen gas, the Magellanic Bridge, the Magellanic Stream, and inside the clouds these interactions trigger bursts of star formation. The gravitational choreography between them is messy, full of near misses and tidal distortions, but the result is clear: compressed gas and new stars. When the clouds began falling into the Milky Way's halo, likely within the last few billion years, the gravitational forces increased further. The Milky Way's mass is enormous. Its tidal influence stirs the clouds, stretches their gas, and funnels some of it inward. This added stress amplifies star formation even more. The Milky Way, in a sense, is squeezing them. Their distorted shapes are the visual evidence. Their starburst regions are the emotional evidence. Every hot, massive star in R136 is a reminder that galaxies don't just orbit peacefully. They interact, collide, reshape one another. The Tarantula Nebula isn't just a natural laboratory for studying young stars. It's a fossil record of galactic relationships written in hydrogen and ultraviolet light. That relationship has other consequences too. As the clouds pass through the Milky Way's halo, they sweep up gas and dust. Some of this material is heated, some stripped away. Their interaction with our halo's dark matter further distorts their internal rotation. These processes create instabilities inside their molecular clouds, instabilities that spark more star formation. The presence of so many young blue massive stars in the LMC is no coincidence. They are the product of environmental pressure from each other, from the Milky Way, from the dynamics of motion through an uneven gravitational field. It's fair to say the Magellanic Clouds are not just galaxies. They are galaxies in motion, galaxies being reshaped, nudged, disturbed, galaxies still evolving. And evolution at the galactic scale often manifests as light, violent, radiant, beautiful light. Inside the Tarantula Nebula, that light is so intense that it strips electrons from atoms, creating the glow we see in photographs. The nebula is bright because the stars inside it are bright, and the stars inside it are bright because the environment is forcing gas to collapse rapidly into massive energetic systems. Nothing comparable exists in the Milky Way today. We had our starburst era billions of years ago. Now we build stars quietly, politely, in small pockets like the Orion Nebula. The Magellanic Clouds are not polite. They are galaxies in their prime, galaxies experiencing tidal stress, galaxies with low metallicity gas that collapses differently than the enriched gas in our own disk. If you want to see what the Milky Way might have looked like in its youth, you look at the LMC. The Tarantula Nebula may be the crown jewel, but across both clouds are signs of stellar diversity. Clusters of ancient red giants sit beside fresh blue clusters only a few million years old. Variable stars, Aurora, Lyrae, Cepheids, give clues to both distance and evolutionary history. The clouds are archives of stellar time, holding snapshots of every stage in the life cycle of stars. But the tarantula is the place where time accelerates, where stars are born fast, burn bright, and die violently. If one of the massive stars in R136 went supernova today, its shockwave would race through the nebula, sculpting new shapes, compressing new regions, and adding another layer to the ongoing story of star birth. And all of it, the chaos, the ultraviolet radiation, the supernova remnants, the gravitational distortions, is contained inside what, to the naked eye, looks like a pale blur in the night sky. The Magellanic Clouds are galaxies pretending to be quiet. Inside them, stars ignite in clusters dense enough to reshape their surroundings. Gas churns. Dark matter molds their motion. And the processes of the early universe continue there, right now in miniature. Two little clouds floating gently beside the Milky Way, and yet, within them, the most dramatic stellar fireworks show in our entire galactic neighbourhood. If the night sky had sound, the Magellanic Clouds would not be silent. They would roar. If you could wipe away the stars and look at the Magellanic Clouds through radio waves instead of visible light, you would see something the naked eye completely hides. The two dwarf galaxies, those pale ghosts drifting beside the Milky Way, are dragging behind them an immense tail of hydrogen gas, a structure so vast it stretches more than 600,000 light-years across the sky. It is called the Magellanic Stream, and it is one of the most spectacular, mysterious, and revealing structures associated with any galaxy in the local group. In visible light, the sky appears clean. But through radio telescopes, the truth spills out. The Magellanic Clouds are shedding material as they move. Their journey is not tidy. It leaves a trail like a comet, except instead of ice and dust. This trail is made of primordial hydrogen gas, stripped and stretched across a swath of space larger than the Milky Way itself. It's strange to imagine that something so enormous could be invisible to us, but hydrogen gas does not glow in optical wavelengths. It emits a faint signature at 21 centimeters, a radio wavelength that passes right through dust and cosmic darkness. Only instruments tuned to that frequency, the giant dishes of radio observatories in Australia, South Africa, Chile, and the United States, can see it clearly. And what they see is astonishing, a river of gas that tells a story of gravitational interaction, tidal forces, and long-term galactic entanglement. The stream begins near the Magellanic Clouds and arcs across the southern sky in a broad, sweeping curve, like a tear in the fabric of intergalactic space. It is not symmetrical. It is not even uniform. Some regions are thick clouds of hydrogen. Others are wisps so faint they can barely be detected. But the message is clear. This structure is the fingerprint of a long and complicated relationship. The presence of the stream alone tells us that the Magellanic Clouds have not travelled peacefully. They have been tugged, stretched, and stripped, mostly by each other and increasingly by the Milky Way. But perhaps even more intriguing than the stream is the Magellanic Bridge, a band of hydrogen gas directly linking the large and small Magellanic Clouds. Think of it as a luminous rope, if only our eyes could see it, pulled taut between two drifting islands of stars. The bridge is not a metaphor. It is literally a physical connection, gas flowing between galaxies. This bridge gives away an ancient secret. It is evidence that the LMC and SMC did not just pass near one another, they interacted closely, possibly colliding around 200 million years ago. A galactic near-miss is not like two asteroids brushing past each other. These are titanic systems, each containing billions of stars, clouds of gas and halos of dark matter. When two galaxies approach, their outer hydrogen clouds feel the tidal pull first. They stretch into filaments, they twist, they funnel material from one to the other. The bridge is the fossil of such an encounter. It hints at a moment when the SMC may have swung close enough to the LMC for their gas envelopes to nearly merge. Stars formed inside the bridge afterward, young bright stars with chemical signatures matching the SMC's gas, born in transit, children of a tidal interaction. And while the bridge connects the two galaxies like a thread, the stream trails behind them like a torn banner, fluttering through the halo of the Milky Way. To understand the stream's existence, astronomers had to build simulations, models of galaxies moving through gravitational fields dominated by dark matter. These simulations show that when two dwarf galaxies orbit near a massive host, the larger galaxy's gravity distorts the path of the smaller ones. It pulls their gas into extended tails that trail behind their motion. The Magellanic System, LMC, SMC, Stream, Bridge, fits this pattern perfectly. Its structure mimics what we would expect from dwarf galaxies that fell into the Milky Way's halo relatively recently. What makes the stream remarkable is its chemical signature. Radio observations reveal that its gas has a metallicity similar to the LMC and SMC, not the Milky Way. That means the stream is not material torn from the Milky Way's halo. It originated within the clouds themselves, pulled out and stretched across space by tidal and hydrodynamic forces. Some portions of the stream match the chemical fingerprint of the SMC. Others match the LMC. This means the stream is a composite, mixed material ripped from both galaxies. The most advanced radio surveys, like those conducted with the Parkes Radio Telescope in Australia, the Arecibo Observatory in Puerto Rico before its collapse, and, more recently, ASCAP and MEERKAT, have shown that the stream contains multiple filaments twisted around each other. These filaments form a braided structure, a kind of double helix of hydrogen stretching behind the clouds. This suggests that the Magellanic Clouds were once gravitationally bound in an orbit around each other, possibly for billions of years, before both began their infall toward the Milky Way. Their interconnected stream is the trail of that shared journey. The story grows even more dramatic when you consider the Milky Way's role. As the clouds fall deeper into our galaxy's halo, they experience ram pressure stripping, a phenomenon where their gas is pushed backward by the hot, diffuse plasma filling the Milky Way's outer halo. Imagine driving a car through fog. The air pushes against the windshield. In galactic terms, the clouds are the car, the halo is the fog, and the stream is what gets blown off. The Magellanic Stream is shaped partly by the gravitational pull of the Milky Way and partly by this hydrodynamic pressure. It is a tug-of-war between gravity and motion. One of the great questions for decades was, why does the stream contain so much gas, more than the LMC and SMC seem to have lost? The answer may lie in the cloud's dark matter halos. If the LMC is wrapped in a massive dark matter cocoon, as recent studies suggest, it can strip gas more efficiently from the SMC. Dark matter, although invisible, forms the gravitational architecture that shapes galaxies. A more massive halo means stronger tidal forces. Stronger tides mean more material pulled off, and the stream becomes richer, denser, longer. The clouds might once have carried far more gas than they have today, and much of that reservoir now drifts behind them, waiting to be pulled into the Milky Way's disk over the coming billions of years. Astronomers suspect that when the stream eventually falls into our galaxy, it could ignite new waves of star formation, like a cosmic rainfall of hydrogen onto a dry landscape. Radio observatories have revealed other details hidden from view. The stream contains clouds of ionized gas, regions where ultraviolet radiation from the Milky Way and the Magellanic Clouds has stripped electrons from hydrogen atoms. It contains neutral hydrogen, cold, dense pockets that could one day collapse into new stars. It contains structures with irregular velocities, some moving faster than others, suggesting that the stream is not a single smooth tail, but a complex, dynamic system. Pieces of the stream even appear to be fragmented, stitched together like drifting patches of intergalactic fog. And yet, despite all this complexity, the stream's origin likely began in a single dramatic moment, a close encounter between the LMC and SMC, amplified later by their plunge toward the Milky Way. The bridge and stream are the visible consequences of invisible forces. To the naked eye, the Magellanic Clouds appear delicate and self-contained. But radio telescopes expose a truth far more dynamic. These galaxies are bleeding gas into space. They are connected by filaments. They are shedding material that stretches almost across the sky's full width. The stream even wraps around the Milky Way, like a ribbon caught in a gravitational wind. Some astronomers describe it as the comet tail of the Magellanic System. Others see it as evidence of the group's shared history, an archaeological record written in hydrogen. But perhaps the most striking thing is that all of this is hidden from ordinary view. You could look at the clouds every night of your life and never know about the river flowing behind them. You could admire their pale glow without ever realizing they leave a trail so vast it dwarfs the Milky Way's disk. Galaxies like to keep secrets. The Magellanic Stream is one of theirs, a whisper of hydrogen stretching across the dark, telling the story of two galaxies pulled apart, pushed together, and carried along by the gravity of a much greater neighbour. Inside those faint smudges in the southern sky lies a journey written not in stars, but in the gas that escaped them, gas that still drifts, still moves, still holds the memory of where the clouds have been and where they are going. A bridge between galaxies, a stream across half the heavens, all invisible except to those who know how to listen. If you picture the Magellanic Clouds orbiting the Milky Way, you might imagine two small galaxies dutifully circling a larger one, like moons tracing a predictable path around a planet. It's a simple image, clean, symmetrical, comforting. But the truth is far stranger. The large and small Magellanic Clouds do not orbit the Milky Way the way the Moon orbits Earth. They do not follow a neat ellipse, nor do they trace out a stable, ancient loop. Their motion is messy, swift, and possibly unprecedented. Instead of being long-term satellites of the Milky Way, they may be new arrivals, plunging into our galaxy's gravitational sphere for the first time in their history. This idea sounds radical, and until recently, no one would have believed it. Astronomers assumed the Magellanic Clouds had been companions of the Milky Way for billions of years, steady neighbours, long-time residents of our galactic suburbs. Then, the Gaia spacecraft changed everything. Launched in 2013, Gaia is the most precise astrometric mission ever built. Its job is to measure the positions and motions of more than 1 billion stars with accuracy down to the micro-arc second. To put that in perspective, Gaia can detect the width of a coin on the surface of the Moon from Earth. This level of precision allows astronomers to track the motions of stars not only in the Milky Way, but also in nearby galaxies, especially the Magellanic Clouds, whose stars are bright enough to be measured cleanly. When Gaia's proper motion data for LMC and SMC stars became available, astronomers realized something astonishing. The clouds are moving much faster than expected. Their tangential velocities, how fast they move across the sky, were far higher than traditional models predicted. The LMC is racing through space at roughly 320 kilometers per second, about 200 miles per second, relative to the Milky Way. The SMC follows close behind, bound not only to the LMC but swept along in its gravitational wake. These velocities are too high for the clouds to be stable long-term satellites. They behave like objects on an infalling trajectory. Galaxies entering the Milky Way's gravitational domain for the first time, not companions that have circled for eons. This first-infall hypothesis emerged around 2007 but gained overwhelming support only after Gaia. The data suggested that the LMC had not completed a single closed orbit around the Milky Way. Instead, it seems to be following a long, sweeping path inward from intergalactic space, possibly as part of a larger group of galaxies. If true, this solves several mysteries at once. It explains why the LMC and SMC appear so dynamic, so warped, so full of recent star formation. Galaxies entering a new gravitational environment experience disturbances. Their gas gets compressed. Their shapes distort, tides stretch them, interactions accelerate internal processes. The Magellanic Clouds look like galaxies in the middle of upheaval, and that's exactly what they would be on their first infall. It also explains the vast Magellanic Stream trailing behind them. The stream's material could have been stripped as the pair plunged into the Milky Way's halo, encountering ram pressure, gravitational torques, and hydrodynamic friction for the first time. The most surprising implication is that the Magellanic Clouds might not have originated near the Milky Way at all. They could have travelled across intergalactic space together for billions of years, bound as a duo, or even as the core of a larger Magellanic group. Small galaxies often form in groups, much like humans form communities. The LMC may be the largest surviving member of such a group. Several ultra-faint dwarf galaxies discovered in the past decade appear to follow similar orbital paths, hinting that they might once have orbited the LMC rather than the Milky Way. This makes the LMC not a simple satellite, but a satellite system within a satellite system, a nested hierarchy of galaxies. But the question remains, are the Magellanic Clouds gravitationally bound to the Milky Way now, or are they passing by on a one-time flyby? The answer depends on something invisible, dark matter. If the Milky Way's dark matter halo is massive enough, perhaps weighing around 1.5 to 2 trillion solar masses, then the LMC is gravitationally captured. Its high speed is simply what you expect when a small galaxy falls into a massive halo for the first time. In that case, the LMC's orbit will eventually circularize, slowing as it loses energy through dynamical friction, and it will one day merge with the Milky Way. But if the Milky Way's halo is lighter, say under 1 trillion solar masses, then the Magellanic Clouds might be only temporarily bound, set to swing around once and escape into intergalactic darkness. The problem is that we still aren't entirely sure how massive the Milky Way actually is. Our galaxy does not come with a scale. Its dark matter halo is vast and diffuse, and direct measurement is nearly impossible. We infer its mass from the motions of stars and satellites, but uncertainties remain large. Interestingly, the presence of the LMC itself complicates these measurements. The LMC is not a passive test particle orbiting a static Milky Way. It is so massive, possibly as much as 250 billion solar masses, including its dark matter halo, that it tugs on the Milky Way in return. The LMC distorts the Milky Way's halo. It shifts the galaxy's centre of mass. It creates a gravitational wake, a ripple in the Milky Way's dark matter, like a boat carving through water. This means the Milky Way is not simply pulling the LMC inward. The LMC is dragging the Milky Way outward. This mutual gravitational dance makes it even harder to determine whether the two galaxies are fully bound. Their motions are not independent. Their orbits are co-created. Still, the best current models suggest the Magellanic Clouds are gravitationally bound and will eventually merge with the Milky Way in a few billion years. Their high speeds are consistent with a first-infall, but their trajectories appear too curved to allow an escape route. They are likely captured, spiralling slowly inward. This has profound implications for the future shape of our galaxy. When the LMC merges with the Milky Way, it will bring its dark matter halo with it. This added mass could trigger new waves of star formation, possibly reshape the structure of the Milky Way's disk, and even shift our galaxy's motion through space. Some simulations show ripples propagating outward across the Milky Way's halo, distortions caused by the LMC's gravitational influence even before the merger begins. These ripples have already been observed in the motions of halo stars measured by Gaia. The halo appears lopsided, asymmetric, disturbed, not the serene spherical structure once imagined. The Magellanic Clouds are already changing the Milky Way. They are warping its outer disk. They are bending its halo. They are pulling its centre of mass. They are carrying their own satellites with them. They are altering the future trajectory of our entire galaxy. Gaia's data also revealed that the clouds are not orbiting the Milky Way independently. The SMC is tightly bound to the LMC, moving in lockstep, despite their intermittent separations and tidal interactions. The LMC is the dominant mass. The SMC is the companion being shepherded along. This explains why the Magellanic Bridge exists. It explains why the SMC is so distorted. It explains why the two galaxies share a gravitational fate. Their orbit around each other is far older than any orbit they have around the Milky Way. When you trace their motion backward using Gaia's measurements, something elegant emerges. A path that winds together like two dancers entering a grand hall only moments ago. The Milky Way is not their home. It is the place they arrived. Their journey has been long, their interaction with each other ancient, their plunge into our galaxy recent. If you could watch their motion over millions of years in time-lapse, you'd see a slow, sweeping curve inward, the LMC pulling the SMC behind it, the Milky Way exerting a deep gravitational pull that bends their path into a graceful arc, not a stable orbit, not a closed loop, but an arrival. One that will eventually end in merger. Understanding this changes more than just the Magellanic Cloud story. It forces us to rethink the nature of the Milky Way's halo. The halo is not a static, undisturbed bubble of dark matter. It is dynamic, reshaped constantly by the infall of satellites. The LMC is the most massive of these satellites, and its influence extends hundreds of thousands of light-years outward. Gaia has shown us that the Milky Way is alive, bending, shifting, responding. The Magellanic Clouds are not ornaments on its edge, they are forces acting upon it. Two galaxies arriving with speed. Two orbits entwined. Two trajectories bent by an invisible halo that holds them now as it once pushed them aside. And all of this, motion, mass, arrival, influence, is contained inside those faint smudges drifting near the southern horizon, hiding the weight of their journey behind a quiet glow. If you look at the Magellanic Clouds, nothing about their faint glow suggests they are carrying enormous gravitational secrets. They look fragile, almost weightless, two pale smudges hanging beneath the Milky Way like drifting mist. But appearances deceive. Beneath their delicate outlines lies a mass of something far heavier than the stars themselves, something invisible, intangible, but undeniably powerful. Dark matter. The Magellanic Clouds are surrounded, shaped and steered by halos of it, vast cocoons of unseen mass that extend tens or even hundreds of thousands of light years beyond the starlit regions we observe. And in recent years, thanks to new measurements from Gaia and deep radio surveys, astronomers have realized something extraordinary. The large Magellanic Cloud appears to have far more dark matter than anyone once believed. This invisible mass changes everything: its history, its orbit, its past relationships, its future destiny, and even the structure of the Milky Way itself. To understand why this matters, it helps to picture the LMC not as the modest dwarf galaxy we see in visible light, but as the bright tip of a colossal iceberg whose true size lies hidden beneath space's surface. The stars we see, scattered irregularly, wrapped around a central bar, represent only a fraction of the galaxy's real mass. Surrounding them is a dark matter halo so immense that it may rival the halos of mid-sized galaxies. Early models estimated the LMC's total mass at around 30 to 50 billion solar masses, significant but small enough for the Milky Way to dominate it without trouble. But Gaia's data, revealing the LMC's surprisingly high velocity, forced astronomers to rethink this. If the LMC had such a small mass, it would have been dramatically slowed by the Milky Way's halo during its approach. Instead, it is still racing along at over 300 kilometers per second. This means the LMC must be more massive, far more massive than previously assumed. Modern simulations suggest a mass closer to 150 to 250 billion solar masses, with the higher estimates gaining increasing support. In other words, the LMC may carry a dark matter halo nearly as massive as 1/4 the mass of the Milky Way's entire stellar disk. The small Magellanic Cloud is smaller, but still substantial, likely wrapped in a halo around 30 billion solar masses. Together, the two form a paired system of dark matter envelopes, intertwined and overlapping, their combined gravity shaping their mutual orbit. This changes the nature of the Magellanic Clouds profoundly. A galaxy with a massive dark matter halo behaves differently. It moves differently. It loses gas differently. It interacts differently. It becomes not a fragile passenger in the Milky Way's outskirts, but a heavyweight contender capable of pushing back, distorting our galaxy, and even dragging smaller galaxies along behind it. And that is exactly what the LMC seems to be doing. The idea that the clouds once belonged to a larger family of galaxies, sometimes called the Magellanic Group, has grown stronger with each new discovery. Around the LMC and SMC, astronomers have found a collection of ultra-faint dwarf galaxies, each with only a few thousand stars. Some are so dim they were invisible until the last decade. Yet they move through space with similar velocities and directions, suggesting they once orbited the LMC as satellites before the group collectively fell into the Milky Way's gravitational well. This idea mirrors a pattern seen throughout the universe. Small galaxies often form around larger dwarfs, creating hierarchies similar to planetary systems. The LMC, if this theory holds, would be the core of such a group. A kind of miniature galaxy cluster carried intact across intergalactic space. For billions of years, this Magellanic group may have drifted alone, far from the gravitational influence of any giant spiral galaxy. It would have been a quiet neighbourhood, a few dwarf galaxies orbiting a larger dwarf, moving together through the cosmic web. Then, perhaps 1 or 2 billion years ago, the group crossed a threshold. It encountered the Milky Way's outer halo, and everything changed. As the LMC and its companions plunged inward, the Milky Way's gravity began stretching them, drawing them into a long arc. Smaller satellites peeled away. Some were captured by the Milky Way directly. Others remained bound to the LMC, but switched to elongated, unstable orbits. Several newly discovered dwarfs, like Hydrus 1, Carina 2, and Carina 3, appear to be strung out along the LMC's orbital path, like beads on a broken necklace. They may be the remnants of that ancient group, survivors of a migration now ending in a collision course. If this is correct, then the Magellanic Clouds are not just two galaxies. They are the heart of a once mighty collective that crossed intergalactic space together, still wrapped in a dark matter cocoon large enough to resist disruption. This would explain why the LMC has not been torn apart by the Milky Way, why the SMC still survives despite repeated encounters, why the Magellanic Stream is so long and rich in gas, why their velocities remain so high, why the Milky Way's halo appears lopsided. The LMC's dark matter halo is so massive that it creates a gravitational wake in the Milky Way's own halo. As the LMC plunges through the dark matter that surrounds our galaxy, it drags some of it along, creating a region of enhanced density behind it. Simulations show that this wake should ripple outward for hundreds of thousands of light years, like the turbulence behind a ship moving through water. And thanks to Gaia's precise measurements of stars in the Milky Way's halo, astronomers have begun to detect exactly such disturbances. The outer regions of the Milky Way appear tilted, stretched, slightly off balance, as if something large is tugging on them. The LMC is that something. It is reshaping the Milky Way in real time. The halo of dark matter that surrounds our galaxy is not fixed. It shifts, oscillates, and deforms in response to incoming masses. The LMC, with its oversized halo, pushes on this structure like a stone dropped into a calm pond. The ripples propagate through the halo, altering the orbits of stars thousands of light years away. This means that the Magellanic Clouds are not simply influenced by the Milky Way, they influence it back. The gravity is mutual. This also complicates the question of whether the clouds are truly bound to the Milky Way or passing by. In classical orbital mechanics, one object orbits another based solely on the mass of the larger. But with the LMC's dark matter halo included, the situation becomes two-sided. Both galaxies orbit their shared centre of mass, which has moved, slightly but measurably, toward the LMC. In a sense, the LMC is dragging the Milky Way off balance. It is as though two dancers have taken each other's hands. The smaller one is still pulled by the larger, but the larger also sways in return. If the LMC lacked such a halo, the Milky Way's centre of mass would remain almost fixed. But with its enormous invisible weight, the LMC forces a shift, and this shift affects everything around it. The orbits of stars, the trajectories of satellite galaxies, even the future of the Milky Way-Andromeda collision billions of years ahead. All of this stems from dark matter, the hidden mass that outnumbers regular matter 5-1 but refuses to glow, shine, or scatter light. We cannot see dark matter directly, but we see its fingerprints. We see the stream, the bridge, the SMC's distortions, the LMC's velocity, the halo wake, the satellite dwarfs stretched along the orbital path. We see the way the Milky Way bends around the LMC's gravity, and from these clues, we reconstruct a picture. The Magellanic System is not small, it is not fragile, it is not temporary, it is vast, heavy, and powerful, carried within a dark matter envelope large enough to reshape one of the largest galaxies in the local group. The faint smudges we see from Earth hide worlds of enormous mass. The LMC may one day merge with the Milky Way, contributing not only its stars and gas, but a rich reservoir of dark matter. This merger could trigger new waves of star formation, distort the spiral arms, perhaps even shift the Milky Way's rotation curve. But even before that distant future arrives, the influence is here, right now, unfolding quietly in the background of the cosmos. Two small galaxies wrapped in dark matter, drifting beside us like unassuming companions, yet carrying enough gravitational presence to stir the halo of the Milky Way and rewrite its structure. The Magellanic Clouds do not merely orbit us, they shape us. They alter us. They tell a story of motion and mass invisible to the eye, but undeniable in its effects. A story written not in starlight, but in the unseen architecture holding the universe together. If you could scoop up a handful of stars from the Magellanic Clouds and analyse what they're made of, you'd notice something immediately. They contain fewer heavy elements than the stars of the Milky Way. Astronomers call this lower metallicity, though the term metallicity in astronomy is deceptive. It doesn't refer to metals in the everyday sense. It refers to all elements heavier than hydrogen and helium, oxygen, carbon, nitrogen, silicon, iron, everything life depends on. Lower metallicity means that the gas forming new stars in the clouds has not been enriched as much by previous generations. It's like comparing a young forest to an ancient one. The young forest will have fewer layers of nutrients in its soil, fewer cycles of decay and regeneration. The older forest, one that has existed for millions of seasons, will have richer, deeper soil. The Milky Way is the old forest. The Magellanic Clouds are still catching up. This difference traces back to star formation history. Galaxies increase their metallicity over time as stars are born, live, die, and return their processed material to the interstellar medium. Every supernova disperses heavy elements. Every dying red giant sheds chemically enriched gas. Slowly, over billions of years, the average composition of the galaxy changes. A galaxy with higher metallicity has experienced more cycles of star birth and death. A galaxy with lower metallicity has lived a quieter life. The large and small Magellanic Clouds have lived quieter lives. Not always quiet. There were bursts, dramatic ones, but overall, they never had the continuous, intense star formation that the Milky Way experienced throughout most of its existence. The clouds formed stars in episodes, short periods of frenetic creation separated by long stretches of relative calm. These starbursts were likely triggered by interactions between the two clouds themselves and by their passages through the Milky Way's halo. Every close approach compressed gas, ignited massive stars, and briefly accelerated chemical enrichment. But between these bursts, enrichment slowed. Heavy elements accumulated more gradually. The result is a chemical profile that looks younger. For example, the average metallicity of the large Magellanic Cloud is roughly half that of the Milky Way's disk. The small Magellanic Cloud is even lower, about 1/5 the Milky Way's metallicity. Yet, despite being chemically young, the clouds contain ancient stars too, old red giants, ancient globular clusters, populations that formed in the early universe. The mixture is unusual. It's a sign that the clouds kept large reservoirs of pristine gas that never fully mixed with the enriched material produced by older stars. These pockets of primordial gas diluted the heavier elements, keeping metallicity low even as new generations were born. In the Milky Way, by contrast, star formation was more sustained and widespread. Its gas was stirred, mixed, and enriched over billions of years. Even older stars in the galactic disk contain more heavy elements than stars of similar age in the clouds. The Milky Way is chemically mature. The clouds are chemically uneven. Astronomers can read this unevenness like a history book. It reveals when star formation accelerated, when gas was stripped, when enrichment stalled, when interactions disturbed the system, and which regions of the clouds formed stars in isolation versus collaboration. Certain clusters in the LMC show ages of 2 billion years, with metallicities expected for galaxies much younger. Other clusters, especially those in the Tarantula Nebula region, are extremely young but sit in gas that still contains surprisingly few heavy elements. This contrast suggests the clouds retained low metallicity gas for long periods, shielding it from enrichment that would have occurred if the galaxies had been more tightly bound to the Milky Way earlier in their history. Chemical evolution can also map interactions. For instance, regions of the SMC near the Magellanic Bridge contain stars enriched by material similar to the LMC, indicating that gas was transferred between them during a close passage. The bridge itself contains young stars, whose metallicity matches the SMC's gas rather than the LMC's, suggesting they formed from stripped material rather than an intermix of both galaxies. It's the chemistry that reveals these stories. Heavy elements are memory, they do not lie. One of the most powerful tools for studying chemical evolution in the Magellanic Clouds is not bright blue giants or ancient red supergiants, but a class of stars that vary in brightness, Cepheid variables. Cepheids pulsate in a predictable rhythm, their brightness rising and falling like a cosmic heartbeat. The period of this pulsation correlates perfectly with their intrinsic luminosity. Measure how fast a cepheid brightens and dims, and you know how bright it should be. Compare that to how bright it appears from Earth, and you get its distance. Cepheids are cosmic yardsticks, precise, dependable, and bright enough to be observed in nearby galaxies. The Magellanic Clouds are full of them. In fact, the very first calibrations of the cosmic distance scale were made using LMC Cepheids in the early 20th century by Henrietta Swan Leavitt. Her discovery of the period luminosity relation using LMC stars became one of the most important stepping stones in all of astronomy, eventually allowing Edwin Hubble to determine the distance to Andromeda and prove that galaxies lie far beyond the Milky Way. Cepheids in the clouds continue to refine our cosmic measurements today. Gaia's data has tightened their calibration even further. Their metallicities reveal how star formation has changed over time. Their ages trace episodes of galactic interaction. Their periods verify distances with incredible precision. But Cepheids are not alone. The clouds also host numerous RR Lyrae variables, ancient pulsating stars older than 10 billion years. RR Lyrae stars represent the oldest populations. They formed when the universe itself was still young. Their presence in both the LMC and SMC shows that these galaxies contain deep, ancient roots beneath their irregular, youthful appearance. By comparing the chemical signatures of Cepheids, RR Lyrae, young clusters, ancient clusters, and field stars, astronomers map the entire evolutionary arc of the clouds. The picture that emerges is one of complexity, episodic formation, tidal interactions, bursts and lulls, pockets of primitive gas, waves of enrichment flowing from one region to another, compared to the Milky Way, whose chemical evolution followed a steadier trajectory. The Magellanic Clouds are chaotic. Their metallicity gradient is patchy. Their enrichment varies from region to region, impacted by collisions, gas flows, and dark matter-driven dynamics. Yet this chemical youthfulness is part of what makes them treasure troves of astrophysics. Their low metallicities mimic the conditions common in galaxies of the early universe. Their star-forming regions provide insight into how massive stars formed when heavy elements were scarce. Their Cepheids refine the distance ladder. Their ancient clusters preserve fossilized information about the first stars. The Magellanic Clouds are, in essence, a laboratory for the study of cosmic evolution. If the Milky Way is a mature tree with rings that record steady growth, the clouds are saplings struck by storms, scarred in some places, flourishing in others, each ring different from the last. Their chemistry is not uniform, but alive. It carries the memory of every birth, every death, every collision, every breath of star-forming gas. And hidden within that chemical story is the truth of their past, written not in words, but in elements forged inside stars long gone, carried forward by those yet to be born. If you could fast forward the night sky a few billion years, speeding time until stars drift like glowing dust on a slow wind, the Magellanic Clouds would no longer appear as faint companions beside the Milky Way. They would be gone, not as vanished ghosts, but as absorbed worlds folded into our galaxy's future. Astronomers believe that the large Magellanic Cloud is on a collision course with the Milky Way. not in the dramatic, catastrophic way Hollywood imagines galaxies colliding, but in the slow, tidal, gravitationally tangled way that galaxies really merge. Over millions of years, through gentle distortions and violent bursts, through ripples in dark matter and waves of starbirth. Simulations suggest that in roughly 2.4 billion years, the centre of the LMC will sink into the Milky Way's halo like a stone settling into deep water. This will not be a sudden impact. It will be a gradual surrender as dynamical friction drains the LMC's orbital energy. Each pass around the Milky Way will be slightly lower, slightly slower, slightly more stretched. Eventually, the smaller galaxy will spiral inward, pulled deeper by the Milky Way's gravity and slowed by the drag of dark matter. The small Magellanic Cloud won't last as long. Simulations predict it will be stripped and absorbed first, likely within 1 billion years, from a combination of tidal forces from both the Milky Way and the LMC. Its stars will disperse throughout the halo, some trailing behind the LMC in long stellar streams, others settling into orbits that reflect its last chaotic encounters. But the central event is the merger of the LMC, and this merger will change the Milky Way in profound, measurable ways. To understand what's coming, astronomers run detailed simulations, billions of particles representing stars, gas, and dark matter, all interacting under gravity. These simulations show that when the LMC merges with the Milky Way, it will add not just stars, but a huge reservoir of dark matter. This addition may be the most transformative part of the collision. Dark matter doesn't glow. It doesn't collide or compress. It doesn't make nebulae or trigger supernovas, but it shapes gravitational landscapes. The LMC's halo could contain around 200 billion solar masses of dark matter. When it merges, this mass will plunge into the Milky Way's halo, shifting the balance of gravity across the outer regions. The Milky Way's centre of mass will move. The halo will stretch and swell. The outer disk will likely warp more dramatically. The motions of thousands of halo stars will change subtly, like dust swirling in a stirred pool. Some simulations suggest the Milky Way could briefly brighten as it digests the LMC's material. Gas stripped from the clouds may rain onto the Milky Way's disk, feeding molecular clouds that have remained quiet for ages. It's possible that the merger will spark a new wave of star formation, lighting up our galaxy with young blue stars for the first time in billions of years. This wouldn't turn the Milky Way into a starburst galaxy, but it would nudge it into a more active mode. The galaxy may look slightly bluer, slightly busier, slightly more alive. The modern Milky Way is mostly a calm, middle-aged spiral. The LMC's arrival could briefly make it feel young again. The interaction may also send ripples through the galactic disk, oscillations that propagate outward like the ringed waves from a stone tossed in a pond. These ripples could trigger star formation along their paths, compressing patches of gas into new clusters. Older stars may find their orbits subtly altered, some flung outward into the halo, others pushed into more elongated paths. Meanwhile, the LMC's own structure will unravel. Its bar, its gas clouds, its Tarantula Nebula, its clusters, even the R136 giants, everything that gives it identity, will be stretched and scattered throughout the Milky Way's inner halo. Some of its stars will blend seamlessly with our own. Others will remain dynamically distinct for billions of years, creating a new stellar population whose origins can be traced long after the merger finishes. In the central regions, dense clusters from the LMC may sink toward the Milky Way's core. Some simulations even suggest the LMC's central black hole, if it has one, might merge with the Milky Way's central supermassive black hole, Sagittarius, a star. Such a merger would emit gravitational waves strong enough to ripple through space-time across the local group. Far from the core, the LMC's outer dark matter halo will mix with the Milky Way's, adding mass that reshapes the distribution of gravity across 500,000 light-years. The result may be visible in the motions of satellite galaxies, in the shape of stellar streams, and in the warping of the outer disk. Meanwhile, the SMC, already weakened by its interactions with the LMC, will not survive. It will dissolve, its stars smeared across space, forming streams that wrap around the Milky Way like pale traces of a story long finished. Some of these stars will join the LMC's debris, others will remain in faint, ghost-like currents flowing through the halo. Eventually, long after the LMC has been absorbed, the Milky Way will move on to the next act of its cosmic life. In roughly the same era, the Andromeda Galaxy will be approaching us. The LMC's arrival will influence that encounter too, altering the Milky Way's mass and shifting its motion slightly, like an early gust of wind before a storm. Galaxies do not collide often in the cosmic timescale of human lives, but they collide regularly in the lifetime of the universe. Every spiral we observe has been shaped by mergers. Every star in the halo is a fossil of collisions past. The Milky Way has absorbed dozens of small galaxies and will absorb dozens more. The Magellanic Clouds are simply the next chapter. Not the final one, not the most dramatic, but one of the most intimate, because they are close enough that we can see them now, hanging quietly in the sky, unaware of the future waiting for them. Nothing about their faint glow suggests the scale of the transformation ahead. Nothing about their gentle shapes hints at the gravitational waves, the future starbirth, the reshaping of the halo, or the stirring of the Milky Way's outer regions. But galaxies are long-lived, and their destinies unfold slowly. One day, the LMC will no longer be a companion, it will be part of us, its stars wandering our sky, its clusters orbiting our core, its gas fueling our next generation of stars, its dark matter halo joining ours in an invisible embrace. And the SMC, long overshadowed by its larger partner, will vanish even earlier, absorbed, stretched, and carried forward into a future where its identity is indistinguishable from the galaxy that consumed it. The night sky will look different then, but the story of the Magellanic Clouds will live on. Not as separate galaxies hanging beside the Milky Way, but as threads woven deeply into our own. For all that we know about the Magellanic Clouds, their distances, their bursts of star formation, the gas they trail behind them, some of the most fundamental questions remain unanswered. These galaxies drift beside us like familiar neighbours, yet their pasts are still partly obscured, wrapped in uncertainty and competing theories. The more we learn, the more elusive their story becomes. One of the greatest mysteries concerns the origin of the Magellanic Stream. This colossal ribbon of hydrogen trailing behind the clouds is so long it spans nearly half the sky, yet astronomers still disagree about how it formed. Some simulations suggest that the stream was pulled from the small Magellanic Cloud by the gravitational tides of the large Magellanic Cloud during a close encounter about 200 million years ago. In this view, the SMC was stripped twice, once by the LMC and once again as the pair fell toward the Milky Way. But other models propose a different history, one where the Milky Way played a far more dominant role. In those scenarios, the stream results from a combination of tidal stripping and ram pressure stripping as the clouds plough through the outer halo of our galaxy. The halo's hot, diffuse gas pushes on the cloud's hydrogen, blowing it backward like wind against a windsock. The truth may be a blend of both ideas, but no single simulation yet captures all the details, the metallicities, the multiple filaments, the ionized structure, the enormous mass of the gas. The stream's complexity outpaces our current models, leaving its origin as one of the Magellanic System's most active research puzzles. There is also uncertainty in the past trajectories of the clouds. With Gaia's exquisite measurements of their proper motions, we know precisely how they're moving now, but reconstructing their past motions is much harder. The Milky Way's own dark matter halo is not static. It deforms and shifts over time, partly because of the LMC's gravitational influence, because the medium through which the clouds travel is constantly changing. Retracing their steps is like trying to follow footprints in wind-blown sand. Some orbital reconstructions suggest that the clouds approached each other as independent dwarfs only a few billion years ago and formed a binary pair that survived long enough to fall into the Milky Way together. Other reconstructions suggest they have been a bound pair since the early universe, travelling together across large-scale cosmic filaments. And a minority of models propose a more dramatic idea, that the clouds might once have belonged to another larger galaxy group and were captured only recently. The uncertainty stems from the fact that we cannot see dark matter directly. Its presence must be inferred, and every change in our estimate of the LMC's halo mass shifts the entire orbital reconstruction. With each new refinement, the path of the clouds through space is redrawn slightly differently, like redrafting a map of ancient trade routes using fragments of pottery and half-legible manuscripts. Another surprising twist in recent years has been the discovery of satellite galaxies orbiting the Magellanic Clouds. For decades, astronomers assumed the LMC and SMC were small enough that they would be satellites of the Milky Way alone, not hosts to their own companions. But survey data, especially from the Dark Energy Survey in Chile, revealed several ultra-faint dwarf galaxies moving in patterns that align closely with the LMC's motion. They travel with it like children following a parent, stretched out along its orbital path. These dwarfs are tiny, some containing only a few thousand stars, but their presence transforms our understanding of the Magellanic System. The LMC may once have been the centre of a group of galaxies, a small cluster of dwarfs that entered the Milky Way as a unit. This idea mirrors what we see elsewhere in the universe. Small galaxies often form in nested families, each bound by its own dark matter cocoon. The clouds themselves carry mysteries written into their shapes. Both galaxies appear irregular, lopsided, and warped, far from the smooth spirals we associate with star systems in balance. Their asymmetry is a sign of repeated tidal encounters, first with each other, then with the Milky Way, and perhaps with other members of their former group. The large Magellanic Cloud's bar sits off-centre, as if tugged sideways by an invisible hand. The small Magellanic Cloud looks torn, stretched into an ellipsoid rather than a disk. Gas from both galaxies has been displaced, leaving trails, bridges, and fragmented structures scattered across space. Their irregularity is not a design flaw. It is the shape of motion, memory, and gravity's endless choreography. And so, the Magellanic Clouds remain partly understood, familiar, close, yet still holding secrets behind their quiet glow. They drift beside us as reminders that even the nearest galaxies can still surprise us, even after centuries of watching the sky. If you stand under a dark southern sky and let your eyes linger on the Magellanic Clouds, there's a quiet realization that settles in. A feeling that the universe, vast and indifferent as it often seems, also contains moments of companionship, not warm in the human sense, not affectionate, but unmistakable in their presence. Two galaxies drifting beside our own, bound not by choice, but by the invisible architectures of gravity. The Milky Way is not alone. It never has been. We often picture galaxies as solitary islands, each spinning in the cosmic ocean, separated by gulfs of emptiness so large they might as well be different universes. But isolation is the exception, not the rule. Most galaxies travel in groups, clusters, and pairs. They form relationships, not emotional ones, but gravitational ones, which endure for billions of years. Companionship at this scale is written in orbits. The Magellanic Clouds are our nearest companions, the galaxies that wander closest to us, circling not in perfect obedience, but in a long, complicated dance. They are not mere satellites. They are participants in a shared gravitational story. Their presence has warped our halo, pulled at our outer disk, shaped the flow of gas in our outskirts, and influenced the orbits of stars. The Milky Way, in turn, has reshaped them, distorting their forms, stirring their gas, guiding their future. It is a relationship built on mutual influence, on invisible forces passing silently between them. When you think about it, galaxies behave less like islands and more like ecosystems, each one filled with billions of stars, clouds, and clusters, and each system interacting with those around it. They respond to pressure, react to collisions, adapt to encounters. They form families, absorb newcomers, and carry histories in their structures. In that sense, the Magellanic Clouds are more than distant objects. They are threads in our galactic story, companions on a shared journey through the larger structure of the universe. There's something poetic in imagining the Milky Way moving through space with smaller galaxies drifting alongside it, quiet escorts that have followed us across millions of years. The clouds orbit in their imperfect loops, leaving trails of hydrogen behind them, marking their path like footprints. They are not static companions, they are travellers. They have their own histories, their own scars, their own restless motions. And yet, here they are, bound to us nevertheless. It's easy to think of gravity as a cold force, a simple law of attraction. But in moments like this, observing how galaxies shape one another, it feels more like a kind of cosmic storytelling, a way in which the universe acknowledges connection. Gravity doesn't care about meaning, but it creates the conditions for meaning to arise. It pulls galaxies together, weaves their trajectories, merges them, scatters their stars, reshapes their futures. In the long arc of cosmic time, the Magellanic Clouds will not remain separate. They will dissolve into the Milky Way, becoming part of our structure. Their stars, their clusters, their histories will blend with ours, and the quiet glow we see today will be only a memory of a time when our galaxy had companions drifting beside it. But for now, they are still there, still close, still moving with us. Silent reminders that even on the scale of galaxies, nothing travels alone.